11 o'clock, so perhaps we can get started. So it's my pleasure to introduce Ivan Dimitrov of Queen's University in Canada, who will give the seminar today. He'll speak about UH free modules over the Lie superalgebra SLMN.
Um, Thank you very much for the invitation. It's with great pleasure that I participate and in this seminar. I wish I were able to attend more of the talks, but because of time difference and other uh, things that come up, I am not as often as I would have liked. So. I'm actually happy to notice that the main driving force behind this talk, behind the results in this talk, Juan Nguyen is also here in the audience, and hopefully there will not be need for him to interfere and correct any errors I make. Uh, so the topic is actually highly, relatively new, highly technical, and quite involved. And I try to design my talk in a way that will give you an idea of what we're studying and what kind of results and what the relationship and motivation for these results is. So I will start from somewhat farther back, and I will be somewhat vague in stating the exact results. As I mentioned, they're quite technical. They involve writing formulas that are long and takes a little bit of time until they become illuminating. So I would probably not aim to state the precise results towards the end of the paper. The results that I'm reporting on are joined with Hua and Charles Paquette and David Wellow from the Royal Military College. They are contained in two papers on the archive, and somehow I consider this talk as kind of an introduction and exposition on these two papers for again and referring to for the more detailed for the kind of more precise details. If you're interested, just email me or Hua for that matter, or consult the papers there. So I'm starting with the motivation, and I'll start with G, which is a simple Lie algebra. And for most of this talk, it is perfectly fine to think of G as being SLM, the Lie algebra of traceless matrices, M by M matrices. Everything is over C in today's talk. And this is a classical object, and we want to study modules over G, or equivalently over U of G, though I realize that this part here is probably not allowed in this seminar because G is perfectly non-associative, but the universal enveloping is associative. Anyway, so historically and naturally, the first type of modules that were considered were finite dimensional. These are extremely well understood. The category of finite dimensional modules is semi-simple, and the simples are very well understood. They are classified by their highest weights. The highest weights, I'm going to mention what the weight is, and highest weight later on. These are dominant highest weights, and this is extremely beautiful first result in representation and structure theory of the algebras. Then beyond the finite dimensional, there are several directions in which of generality. I think the most natural next direction is highest weight models. And in fact, they appear already in studying the finite dimensional models. Naturally, at some point, one has to turn to highest weight models that are not necessarily finite dimensional. Consider the Verma models, the unique quotients, and then study when the unique irreducible quotient is actually finite dimensional. But highest weight models have their rich theory on their own. This is the category O theory, which includes Kashdan-Lustig polynomials and so on. And this is also a very well understood subject. Another direction that comes after finite dimensional models is if we're thinking more of models coming from the corresponding Lie group, and the Lie group is not compact, then naturally the category of Harish-Chandra models appears. I am putting here a different symbol, this star, just to emphasize that I'm not going to go in this direction of discussion. I'm just thinking of going along the line of finite dimensional highest weight models and so on. And then the next, beyond highest weight models, the next is weight model. So I'm going to mention something about what a highest weight model is. G, if I take a Cartan subalgebra H, then G decomposes as the direct sum of H and the direct sum of all weight space, root spaces of G. Here, delta is a subspace of subset of H star is the root system. And M is weight module. If it is semi-simple with respect to H, so M is a G module, but I can consider it as a module over H, and I ask that it is semi-simple module over H, meaning that M is the direct sum M lambda for some elements of H dual, where M lambda is just the eigenspace corresponding to lambda. Hm is lambda of Hm for every H and H. I did not define here the root space decomposition. This is just another name for saying that G itself is a weight module with respect to H, and these are the corresponding weight spaces, which for historical reasons are called root spaces. If I have a weight module, the support of M is just all lambda in H star such that M lambda is not zero. If X is in G alpha and M is in M lambda, then acting on M by X gets me in M lambda plus alpha. Of course, it may be zero. This is this very easy formula makes studying weight models much simpler. And all finite dimensional modules are weight modules with respect to every Cartan subalgebra. And moreover, the weights are naturally have a structure of a partially ordered set, and they are highest weight modules, meaning that with respect to the natural order that comes from taking basis of the root system, there is a maximal weight. Then the highest weight modules are the ones that have that are weight modules and that have a maximal weight. For the category one has to allow sums of such modules. As you can see, and the support of a finite dimensional module is very easy to describe. It is actually the convex, the intersection of the convex hull of the orbit of the highest weight with the shift by the root lattice. The highest weight, the support of Verma module, which is the universal highest weight module, is also very easy to describe. And the supports of the categorical modules are not so difficult to describe. Their exact multiplicities are given by the Kazhdan-Lustig polynomials and so on. So in this line of modules, finite dimensional highest weight, then naturally comes the question of study weight modules. Sorry, study weight modules. But unfortunately, this is too difficult a problem. Maybe it is beyond reach. However, if we put the restriction with finite dimensional weight spaces, meaning that M itself may be infinite dimensional, but this would be due to the fact that the support is infinite, while each of the individual spaces M lambda are finite dimensional. And these are completely classified, the irreducible ones. So here, irreducible, those are classified. And there are two steps in this. The first is the Fernando-Futorni parabolic induction theorem, which tells us that every such module is induced from a module which is called by Mathieu, and the second part is classification of cuspidal modules by Mathieu. A module is cuspidal if all x alpha in G alpha act freely. Injectively, all right, but this is the same as freely. So all root vectors act freely on the module. So if a root vector doesn't act freely, then we can actually obtain a subalgebra of G from which that module would be induced. And in this classification, the finite dimensionals, in this scheme, the finite dimensionals are the ones where no X alpha acts injectively, meaning that we're inducing just from a module over the Cartan, and this is what a weight module is. So of these two results, I'm going to actually focus on the second one, on the classification by Mathieu. Already Fernando proved that cuspidal modules exist only for type A and C. AL, which is SL plus 1, and CL, and classified, and Mathieu classified them. This is a result of Fernando, actually. And Mathieu classified them. The main tool is the following definition, the following idea of coherent family. Coherent family is M, which I'm not going to provide the full definition again, but I'm trying to give you the idea of what a coherent family is. Coherent family M is first a weight module with finite dimensional weight spaces and support, which is the whole dual space of H. The second condition is M has a central character. I.e., elements of Z, the center of the universal enveloping, act by scalars. And the third condition, which is very natural, a little bit technical, there is compatibility condition. I'm not going to say exactly what the compatibility condition is, but I'm going to say what I mean by the compatibility condition. So suppose M is a coherent family, then M is the direct sum of M nu, where nu, M nu itself is the direct sum of M lambda for lambda in nu, and here nu is in H star quotient by the root lattice. So the point of this, what I'm saying is, according to the formula of the action here, if I start with a weight vector in one weight space, I can only move to vectors in weight spaces that differ by roots. So if I start with any weight vector in weight module, the module that will be generated by that vector would have weights that are only in the translate of this weight by the root lattice, which means that immediately in a coherent family, it decomposes as a direct sum of G submodules. And they are actually this is an uncountable set here. So this is an uncountable direct sum of submodule, which seems counterintuitive. We're trying to actually classify all the irreducibles, and instead we're going to some humongous thing, which is already, we know, is direct sum of uncountably many modules. And the compatibility is the following. If I look at these models here, they have nothing to do with each other. So in order to put them in one family, I have to somehow link them in some way. And the compatibility condition is actually a condition that the trace of the elements of the centralizer of H in the universal enveloping algebra, the trace of such elements are polynomials of lambda. And that is the compatibility condition for a coherent family. But the important thing is, if I have a coherent family, if M is a coherent family, again, I'm a bit imprecise here because obviously the direct sum of two coherent families is a coherent family, but we can easily define what an irreducible coherent family is, one that does not break further down into irreducibles. If M is a coherent family, then first, most M nu are irreducible. And secondly, the rest are identifiable by models by highest weight models. And in fact, by finite dimensional models. So we have this really beautiful picture. The classification that we already have of finite dimensional models, not all of them, some very special finite dimensional models, gives us classification of the coherent families, because what finite dimensional models appear in a coherent family, they would not appear as mu nu, they would appear as subquotients in mu nu, m nu here. They determine M, the whole coherent family, and most of the summands of M are irreducible, who actually Mateo points out which ones are irreducible, and the irreducible ones actually exhaust all the irreducible Cuspidal models. This is the idea of the classification provided by Mateo. And it's extremely beautiful result. Now, I want to mention one thing here. Actually, yeah, one remark. Coherent families of rank 1 are very easy to understand. Now, I did not define rank. A rank of a coherent family is the dimension of each of the weight spaces. It follows easily from the definition here that all the weight spaces of a coherent family have the same dimension. So the ones of rank 1 are very easy to understand, and actually they're essentially shifted polynomial or shifted to Uram polynomials in variables x1 to xn plus 1, and then Britton and Lemire this is a step that I did not mention between in the previous page between Fernando Futorni's parabolic induction theorem and Mattel's classification, Britton and Lemire classified the cuspidal models of rank for which the dimension of the weight spaces is 1. Classified cuspidal with dimension m lambda equal 1, and conjectured that any cuspidal is a submodel of such of cuspidal of rank 1 rank equal 1 and submodel of tensor product of cuspidal of rank 1 and finite dimensional model. And in fact, it is not extremely difficult to actually see what the decompositions of these tensor products are. So if this conjecture were proved, Britton and Lemire would have a classification. This conjecture was proved, but it was proved using Mattel's classification. So even though this is not the way to classify cuspidal models, it is still a very good way to think about cuspidal models. Okay, so this is enough about cuspidal models, about weight models. And I'm now switching to something that seems to be exactly on the opposite end of weight models. So the second part would be UH3 models. After I'm going to mention some results that, as far as I'm aware, they are results of Jonathan Nielsen. So a G model, well, this is unnecessary. It's unnecessary to give this definition. We're going to consider G models which are free under the universal enveloping of UH. Notice that H is abelian. H is the span of, say, x1, x2, xn. And then UH is just the polynomial algebra of these variables x1 to xn. So so the point is we consider models that are instead of semi-simple over H, they are free over H. This seems to be the extremely opposite end of models as far as the action of H is concerned. And Nielsen introduced the weighting functor actually he acknowledges Mattel for the suggestion for the weighting functor W from UH3 models. Sorry, it is actually from G models to weight models. So this is a very natural, once you see it, it is extremely natural functor that takes any model and makes the weight model. Take the model M, and to the model M you assign the model WM, which is simply you force splitting it into weight spaces. So it is the direct sum of the quotients of m by the module m by mm, where m is a maximal ideal of u of h. And because u of h is a polynomial algebra, this is just the direct sum over elements of the dual lambda m quotient by the kernel of lambda m, where I am here actually abusing notation where I use lambda both for an element of the dual and its extension. This lambda is an algebra homomorphism which extends lambda defined on just h. So as you can see, what is happening here, we're just taking m, and for each point in the affine space, we're taking a weight space, forcing such a weight space, and the action of an element x alpha acting on v plus the kernel of lambda m, by definition, is you act by x alpha on v plus the kernel. However, you move it according to the rule for action on weight spaces. So there is nothing you can do about the action of x lambda on the class of v, but use the action of x alpha on v, except you know that in a weight module, if this is in the weight space m lambda, this should be in the weight space lambda plus alpha. And that is the weighting functor. So the properties of the weighting functor. I'm going to list some properties. First, the weighting functor applied twice is the same as being applied once. Secondly, some of these fall from one another. So Wm is a weight module. Something that follows from the combination of the two. If M is a weight module, hence Wm is just M. That follows from the previous ones. The weighting functor preserves the central character. If M has its central character, so does Wm, and they are the same. So this is not the most clear English language, but I think it is. My intention is clear, hopefully. And the most important property here, which is relevant to the discussion, if M is UH-free, then Wm is a coherent family. So this is another way of constructing and explaining where coherent families come from. Moreover, and now you actually see this kind of parallel. In order to classify the reducible cuspidal modules, Mathieu defines coherent families that are extremely large and packs together a lot of irreducibles together. And similar thing, in order to get coherent families here, we start with some model that is extremely large. Well, it's not extremely large, but it is very far away from being a weight model, and force a weight model. And because in the weighting functor, the model which is obtained as a result of applying the weighting functor to UH3 model has a full support, the whole dual of H, we actually have a chance of getting a coherent family, and it turns out we do get a coherent family. And in fact, here the rank and the ranks are preserved. So if M is UH3 of rank D, WM, the weight space of WM have all dimension D. So there is this in there. Further, Nielsen further classified all UH3 of rank 1 over SON plus described the Holder series plus and the proved Klebsch-Gordon type for SO2, formula for the tensor product of M tensor E, where M is UH3 of rank 1, and this is finite dimension. So the same, we see another parallel here. This is with the conjecture of Britton and Lemire, and again, we're getting UH3 of rank 1, understanding them, and by tensoring by finite dimensional models, we get UH3 of higher ranks. So as a final remark here, beyond UH3 beyond rank 1 is very difficult. And I'm not actually honest, it is not just difficult, it is very difficult. Some constructions exist, consistent constructions, but classification is elusive. They seem to have, there seem to be new phenomena appearing in terms of reducibility and so on and so forth. So this is how much I'm going to say about this. Again, the topic of UH3 models over Lie algebras is very active, and there are many interesting and deep results, but I'll stop here. Next, what about superalgebras? And here I'm going to consider G just be SLMN. Again, one can study all classical superalgebras, MN, OSP, the exceptional ones, maybe including P or Q, all of these are pretty open. So the first step in the first work was and Zhao, which proved that rank 1 UH3 modules exist only for OSP 1 to M. Now, I said that G is SLMN, but this is a result for the classical one. So so let me put the SLMN later. So G here is SLMN, OSP N to N, dot, dot, dot. So this result is an excellent observation. However, it is not surprising. So explanation that one can give, and the proof is not much more than this explanation, is that H is even, and hence UH is even, hence a rank 1 UH3 module would not have a natural Z2 grading. And this already makes it somewhat undesirable from the point of Lie superalgebras, because Lie superalgebra is Z2 graded, and it is natural to look for representations and so on that are in the Z2 graded category. This is not a proof. The proof, the other part of the explanation, so I'm giving you somehow intuitive explanation. The other part is that in a Lie algebra, rank 1 subalgebras, semi-simple, simple rank 1 subalgebras are isomorphic to SL2. In a superalgebra, rank 1 subalgebras are isomorphic to one of the SL2, OSP12, or SL11. And if I look at SL11 and try to write down rank 1 UH3 over SL11, now I have to tell what SL11 is. SL11 is the span of 3 elements, X, Y, and H. X and Y are odd. H is even. X, Y, the commutator of X, Y is H, but H is in the center. So in a rank 1 UH3 module over SL1, I can look at how X acts on the vector 1, because I'm thinking of this module as C of H, this element H. H acting on 1 would be P of H. Y acting on 1 would be Q of H. x squared, which is 1/2 the commutator of x and x, must be 0. Hence, we would have p squared equal q squared equal 0. On the other hand, x y plus yx equal h would imply pq plus qp equal h, which of course is impossible because p squared equal q squared equals 0 and pq plus qp equal h is impossible for polynomials p and q. Now, how does this explain Chi and Zhao's result? Well, OSP1 to M is the only superalgebra that does not have a subalgebra isomorphic to SL11. All the other, all the subalgebras of rank 1 of OSP1 to M are of this form, and all other subalgebras in this list that I did not exactly clarify, for which the theorem, Chi and Zhao's theorem apply, they do have such subalgebras. And this is basically the proof. So this led us to the question of, this would be part 4, study rank 2 and higher for G equal SLMN. And this is these are the results that I'm going to present here. So this is somehow how we got to this, and this is the problem that we're studying. And as a first step, which would be number 4 here, which is a baby step, we want to consider SLG to be SL11. And we want to consider rank equal to. So we're looking for models of UH3 models of rank 2. So again, if I write down that my module is CH plus CH, and I define P of H to be the matrix X acting on 1, 0, X acting on 0, 1. So this is a 2x2 matrix with entries in polynomials on H, and QH to be the similar matrix for Y. Then we get for P and Q to define, let me say one more thing. I'm skipping a lot of calculations here, but let me not skip this one. Then I know completely the action of X on any vector in the space M, namely f of h, g of h. That would be simply multiplying this, is simply multiplication by p, and similarly the action of y is multiplication by q. Which leads me to the fact that p and q define SL11 module, which is necessarily UA3, because this is how we define it. If and only if we have p squared equal squared and equals 0, and QH PH plus PH QH equals H times empty matrix. And item that is not difficult is that theorem any such M is isomorphic to M of, and here I'm writing just the matrices P and Q. So the model depends on these two matrices P and Q, and I'm just writing them 0, 1, 0, 0, 0, 0, H, 0, or M of 0, 8, 0, 0, 0, 0, 1, 0. And these two are isomorphic. So this is a classification of SL11 models. This is a fairly simple result. The point of this result is that it tells us two things. There are models of rank 2. They are very easy to classify. And moreover, notice that I did not impose a condition on these models. They automatically are naturally Z2 graded because X and Y can be written as upper and lower triangular matrices, and then it is natural to take the two components here, this to be the zero, the even component and the odd component. So when I said that any such M is isomorphic, there are conjugations that would change the matrices that come in here. So if I start with arbitrary M, that is direct sum of CH and CH, and look for all solutions of P and Q, there would be P and Q that are not graded, but they are conjugate to graded. So there is a natural grading of such models, Z to grade. So the next actually is to look at the Lie algebra SL-M1, and we're still working in rank 2. We're looking for rank 2 models. Here H is the span of H1, H2, Hm. These are still even variables, meaning that UH is the polynomial algebra of, I'm going to write H underlined for this M tuple, and we're looking for M, which is the direct sum of CH. This is the place where I'm going to write a few formulas. So for I and j in the set 1 to m, 1 bar. So 1 bar corresponds to the odd part of the natural representation, and the m correspond to the even part. I define matrices Eij, which are similar to the matrices P and Q. So they are Eij 1, 0, Eij 0, 1. These are again 2 by 2 matrices with entries in CH. So now the point is there everything is similar, except the ring here becomes even more complicated, because before it was the ring of polynomials of one variable, so at least it was a principal ideal domain. Now it is the ring of polynomials over several variables, so it is only unique factorization domain. And then I can define for f of h, which belongs is space ch plus ch, I can prove that eij fh is eij h sigma j inverse f of h. So this is a very similar formula to the previous one. It tells me that if I know the action of an element on the basic vectors, I know the action on the whole polynomial, which is obvious because the polynomial, the model is generated by these basic elements. The only thing is that these unpleasant shifts appear here. What these shifts are, sigma I of f of h is f of h1 and so on, and I shift hi by 1. So sigma I is the shift of the ith variable by 1. And so here I have to be shifting when I act by ej, I have to shift the jth variable forward by 1 and the ith variable backward by 1. And this is if I and j are between 1 and 10. If one of them is 1 bar, there is a different corresponding shift. I shift all of them. So I don't want to go into the formulas. I'm running out of time, and the formulas are illuminating only after you've actually carefully read them. And so I don't think there is much point in doing this. So now the theorem that we have is, let me take A to be an n tuple, A1, A2, Am in the m-dimensional torus. Let me take S to be a subset of the indices 1 to m. And let me define the matrices Eij in the following way. Ei 1 bar is 0 Ai Hi 0 0. E 1 bar I to be 0 0 Ai inverse 0 if I is in S, and if I is not in S, I define them I put the H in the second matrix. This S corresponds to actually an automorphism of the Lie algebra. These matrices generate the whole algebra. So if I know these matrices, I know the whole equation. And hence, these matrices define a model M in M of AS of UH free of rank 2. So the theorem is then first, every UH free Frank 2 is isomorphic to MAS for some A and S. Secondly, I know the isomorphisms. These parameters are very A to S2. If and only if the S are the same, S1 is the same as S2, and A1 and A2 are the same in the projective space. So they're not the same in the affine, but in the projective space. And as a consequence of this, also we know the structure of these models. AMS is indecomposable. I'm about to finish. Of finite length. So two remarks before I stop. This classification tells us that every module of rank 2 is naturally Z2 graded. So we do not have to start looking at Z2 graded models, but UH3 models of rank 2 are naturally Z2 graded. And the second thing, which is interesting, is if I want to go beyond SLM1 to SLMN, where both M and N are at least 2, there are no models of rank 2. We need to look for higher rank for UH3 models. With this, I'll end because I'm out of time, and I'll be happy to answer any questions.
Yes. Thank you, Ivan. Are there any questions for Ivan? I had a couple not just general questions about the weighting functor, which you gave such a nice overview of. So if I understand correctly, what the weighting functor is really doing is killing off the torsion points in the module. So a UH3, you're getting everything. The other extreme, at a weight module, you're only retaining specifically the weight spaces. So whenever you have a sort of torsion action of element of the Cartan, you're just, let's see, you're sort of killing off these points.
What do you mean by torsion action? On the weight models, it is a torsion action of the.
That's true. Yeah, then in the weight modules, you're not killing off those weight spaces. I'm just trying to understand what's happening here.
It is reproducing. If you have the whole model, it is kind of reproducing it for each weight space, and then killing off the action and making it act by a scalar. So I'm thinking of first I have the model, and I then smear it so that for every element of the dual space I have one copy of that model.
Right.
This is enormous, and then for each of those copies I just make it I force H to act by the scalar.
And then if incompatible, then that piece dies.
Then it dies.
Yeah, I see.
Yeah. So for UH3 model, all of them would be compatible. For weight models, only in the weight space they will be compatible. Yeah.
So this question of trying to figure out what the higher ranked UH3 modules are, you're really looking at, you want to find the pre-images under the weighting functor of things that look like pointed module, meaning dimension 1 weight spaces tensor with a finite dimensional module.
Yeah, well, I have to be careful here. the tensor products, they don't central really. So it is more delicate there. You take a rank one, you tensor it, it decomposes according to the central characters, and then you probably want to take the preimages of what happens on each of the components. And these the ones with the central character.
Blocks there for the weight modules, so you can just take the blocks according to the central characters. I see.
Yeah. It seems like, this is what the theorem says, and this is what it states. But for some reason, it doesn't give us much clarity, because after all, the coherent families are quite, the tensor product realization is not very explicit. Because essentially in Mateos classification, it is the tensor product realization. No.
Are there some other questions for Ivan? I think I see someone has put something in chat. Let's see.
Oh, okay.
Oh, just saying thank you. Okay, no, not a question. Okay.
I have a question. If Hua wants to make a short comment, correct anything I said, or
no, I think everything is good. Yeah, it's just like the thing of weighting functor is the functor is not exact, so it's kind of hidden the family, the UH-free module. So like you kind of like you should think about it kind of like a bundle, like a UH-free module, and you smash it down into like a weight module in the base, like, and it's hidden a lot of things. Yeah, and we actually have a paper coming out explaining this phenomena. Yeah.
Right. This actually explains it. So the claim is only in one direction. I have the weighting functor, and the result is such. But if I apply it, if I know what the result is, where I started, is not clear.
Okay. Well, let's thank Ivan again for very nice and clear talk.
And thank you for your patience and attention.
Okay. Goodbye.
Bye.